Okay, good morning, welcome back. Happy Monday. Take one of our last looks at the calendar. We have 3 more days of new material. That's all 3 classes this week. Then a week from today, Monday, May the 12th, we have our 5th and final quest, which is just on the stuff since the last test, only the fraction stuff starting last Friday. And then a week from this coming Wednesday is our review day. For the final exam, and then our exam itself is on Monday, May 19th. 2 weeks from today, this course will be finished. Questions on the calendar? Not a bad idea to make a note in your calendar that May 19th is our final exam, 8 until 10, right here in this room. Okay? All right, so let's jump here to page 77. Up at the top, we'll first refresh our memory. On Friday, our last class, we started playing with algebraic fractions. They're like normal fractions, except instead of just numbers, they also have variables in them. And we did 2 things with those fractions. Number 1, we learned how to reduce them. And the idea was that you can only reduce if you see what operation? Multiplication. You cannot reduce over addition. You cannot reduce over subtraction. But if you see multiplication and only multiplication, you can cancel things that look exactly the same. And that meant that we spent a lot of time at the start of these problems by turning them into multiplication. How did we turn things into multiplication? We factored. So the first step last class was to factor everything. And pretty much that's going to be the first step in this class too. Okay, and then after we learned how to simplify solitary fractions, we then started combining 2 fractions. We saw how to multiply fractions, and we saw how to divide them. And they work exactly the same as multiplying and dividing ordinary fractions, but the idea was to factor everything and reduce before you do your multiplication. So today is our first day on addition and subtraction. So let's take a look at adding 2 ordinary fractions just with numbers. 2/3 plus 5/3. Now I know that you know the answer is 7/3, but what are you really doing? You're really saying, well, they have exactly the same denominator. So you copy that denominator, right? We're not adding the 3 plus the 3 to make a 6 in the bottom. And then upstairs, you're just putting them together as 1 fraction. And even if you don't visualize it that way, that's really what you're doing. You know the answer is 7/3, but really what you're saying is I get to add the 2 things on the top and I copy the thing on the bottom. And it's going to work exactly the same here for fractions with x in it. So for example, down here in number 2, part A, 3x over 2 plus x over 2. What's good about those 2 fractions? Common denominator. It's already there, so you don't have to do anything. So what that means is that the new denominator is going to be 2. And then to make the numerator, I'm just going to write the things that were in the numerator before. And then we combine terms if possible. So upstairs, 4x. Am I allowed to cancel the 4 with the 2? Why? It's multiplication. That dot right there says yes, you can cancel. So this one here is just 2x. Okay, let's try, we'll jump down here to part C. First thing we see is what's the operation between the 2 fractions? Addition. Next thing we look at is the denominators. Are we happy or sad looking at these denominators? Very happy because they're the same, which means we can just mush them together. So the new denominator is going to be x plus 2. The whole thing just gets copied. No funny business. And then the new numerator is just the 2 numerators we had, 2x minus 5, x plus 4, with what in between? Addition. Just bringing those guys over. Now I'm going to put something in that isn't mandatory here, but will be in very similar looking problems. I'm going to put this, parentheses. And those parentheses aren't coming from nowhere. I mean, technically there are parentheses around each of these numerators. The division, the fraction line tells you that that numerator is one thing. And so it's not required to put parentheses there, but they're implied, right? That fraction line gives you a way to think about everything upstairs as being one thing. Now, they're not necessary in this problem, but they will be in the one we're about to do. So I'd encourage you to just put them. So why didn't I put them up here? Well, I could have put them up here. But 3x and x are just single terms by themselves, and there's no way we can get anything wrong without those parentheses. So let's come down here and finish this one. Like I said, the parentheses are not relevant in this problem. We can ignore them. So we're just going to combine the x's. How many? 3x, and then we'll combine the numbers. Minus 1, divide by x plus 2. Questions on that? We can cancel the x's, right? And just get rid of those. What's that? Alan's asking if we can do that. Are we allowed to do that? Yeah, 3 times x is multiplication. Okay? That's right. You can't ignore the subtraction of 1 up there. Yes, there is a multiplication, but the main thing upstairs is a subtraction. And we said this last time, you cannot pick and choose when you're canceling. Or if it looked like 3x times negative 1, then it would be okay. If it's multiplication, then it's ready to cancel. But we cannot cancel because that is a subtraction on top. Likewise, the x on the bottom is not ready to cancel because it's next to an addition sign. Victor? Yes, you can cancel the 3's. You could also cancel the x's. But is here? Now we can't cancel anything. Nope. Because now the top is a subtraction. Whereas before, the first thing you gave me, it was a multiplication. Yeah. But this is now a subtraction problem. There's a multiplication in it, but you can't pick and choose. It is subtraction. So it's not cancelable. So that one's done. 3x minus 1 over x plus 2. Nothing else to do there. Let's jump to the last one in the table, part F. What's the main operation here for the two fractions? Subtraction. So we look at the denominators. Do they make us happy or sad? Happy because they're the same. Doesn't matter how complicated they are. All we care about is that they're the same. So the new denominator is going to be x minus 1. And then we'll take our numerators and put them here under one fraction, copying them just like they are. What symbol goes between? Subtraction, because this was a subtraction of two fractions. And I promise you, if you do the problem as it sits now, you'll get the wrong answer. What do we need? Parentheses. We've got to have parentheses here. So first of all, do you guys agree that this will be a different answer than the one that we had before the parentheses? Because now that subtraction symbol is going to carry through into the subtract 5 over here. It's going to change things. So why is this right and the other one was wrong? Well, take a look. This subtraction symbol says I'm going to subtract this entire fraction, right? I'm going to subtract a 3x and I'm going to subtract a minus 5. But if you don't have those parentheses there, then all you're doing is subtracting the 3x. You're not subtracting the negative 5. So we got to have the parentheses, and that's why I put them up in this previous problem, even though we didn't need them. With addition, you don't need them, but I'd rather you put them too often than not often enough. You always need them for subtraction, so let's just put them for both addition and subtraction, and then we'll always have them when we need them. Okay, so this guy equals, the x minus 3 we can copy, minus 3x, and then what happens when I do this minus negative 5 becomes plus 5. That's the real common mistake to make, to forget that change of sign. Because this minus sign right here comes in and hits both of these guys. It's like an invisible -1 times. So that -1 is going to come in and change all the signs inside. Okay, and now we'll mush the like terms together. So the x minus 3x gives -2x. Minus 3 plus 5 gives +2. I mean, it kind of does disappear, but what do you get when you distribute that -1 into this guy? -3x, right, which we have here. Okay, normally we'd be done, but if you can reduce, you must. You have to reduce as far as is possible. Can I cancel anything right now? What's the main operation upstairs? It's a plus, it's addition. It's not cancelable. Downstairs, it's a minus. Can't cancel anything. But if you factor, then you can turn things into multiplication, and then maybe we can cancel. What can you factor out on top? 2. Let's factor out a 2 on top, just to see what happens. Most likely nothing happens, but it's worth a look. So 2 comes out. What's left in the first term? -x plus 1. You guys buy it? Okay, and then the last observation here is the thing in the parentheses is kind of starting to look a lot like the thing downstairs. They're not exactly the same. But if I write this, you guys buy the thing in the parentheses is exactly the same as 1 minus x? And it's +1 and it's a -x. I'm just rewriting it, different order, but it's the same thing. So if on top you have a 1 minus x and the bottom you have an x minus 1, you can cancel, but it's -1. This is the -1 thing. You guys remember? A minus b over b minus a. Cross them off, but introduce a -1. So this guy, and then it becomes a -1 up here. So the final answer is just that 2 times the -1 that was left over when you cancel. So we just get -2. Any questions on that one? Okay, so we handled addition and subtraction when they have the same denominator. What's the more complicated thing we haven't handled? Is when they have different denominators. So let's take a look on the next page. And we're going to do this problem right here, 9 over 28 plus 3 over 20. And these are just ordinary fractions with ordinary numbers. So you could probably do this without any process that we're about to go through. But we're going to go through this very detailed process for an easy problem because the process will apply just as well to the hard problems. So forget the crazy diagrams that we've got here, but 28 and 20. Okay, can you look at those and figure out what the lowest common denominator is, or is that tough? What's that? 140 is one vote. All right, so does 20 go into 140? It does. So then we're hoping that 28 goes into 140. I don't know if it does. Yeah, let's see, 5 28s. Is that it? I think 28 goes in to 145 times. Brandon, how'd you get 140? Yeah, and so like if the numbers are small enough, you might have some miracle. Those numbers are not small enough. 140 is the correct lowest common denominator. I would have struggled and taken a lot longer to find it than Brandon did. But if it was something like, I don't know, 4 and 6, what's the LCD of 4 and 6? It's 12, right? So if the numbers are small, you guys can just figure them out. If they're bigger, it's more work. But I'm going to give you a process that that will apply no matter what the numbers are, and even if there's x's in them. So step 1 says factor all denominators completely. So we're going to take 28 and we're going to factor it. So 28 is really something times something times. So what is 28 equal to? So it's 14 times 2. That's one way to factor it. But 14 you can factor further than 7 and 2. So would you guys agree that 28 is really 7 times 2 times 2? And we can't factor any further because 7, 2, and 2 are what kind of numbers? They're prime numbers. They have no other factors. Okay, next thing is the same game, but for the number 20. So it doesn't matter how you start to factor it. You can call it 4 times 5 or 10 times 2. Either way, if you get all the way down to primes, you will always get to the same thing. So here is 2 times 2 times 5. It's okay? Just as a quick aside, the fact that you always get to the same thing, regardless of how you start factoring, is an important result in math. Like if we had gone to 10 and 2 instead of 4 and 5, you'd still get to the same 2 times 2 times 5. And that theorem is called the fundamental theorem of arithmetic. I'll give you the name again, the fundamental theorem of arithmetic. How many fundamental theorems of arithmetic do you think there are? There's one, is this one. The fact that we call it the fundamental theorem of all of arithmetic gives you a sense of how important it is to mathematicians. Okay, but coming back here, we go to step 2, which relates to this funny thing called the Venn diagram. You guys seen those before? So what we're going to do is put the factors for each denominator into a Venn diagram, but we want to be sure to put the common factors into the overlapping space. So the first thing I see in the 7 times 2 times 2 is a 7. Do you see that 7 in the other set of numbers? No. So I'm going to put the 7 over there. And maybe I'll put check marks to say, yes, I've dealt with it. So that 7 is handled. And then the next thing we see is a 2. Do you see a 2 in the other one? We do. So I'm going to put that 2 in the overlapping space, and I'm going to check off a 2 that's in both of them, right? 1, 2 from each list. The next thing I see in purple is another 2. Is there another 2 in the other list? There is. So that also is in common. Check off another 2 from each one. I've finished with the purple. Coming over here to blue, what's still unchecked? The 5. Is there a 5 in the purple? No. So that means the 5 goes into the other, like the complete other set. And if we just put dots between all of these numbers, 7 times 2 times 2 times 5, that's the lowest common denominator. 7 times 2 times 2 times 5. Any questions on how we filled in that diagram? Because that's a big part of this process. The idea is you got to put every factor that you see, but if you see factors that are in common, you don't need to include them twice. You just include them the one time, and that's the overlapping space. Okay, step 3. Find the lowest common denominator, abbreviated LCD, by multiplying together all the factors that appear anywhere in the Venn diagram. So I'm just going to write down here 7 times 2 times 2 times 5. Now, if you're doing this arithmetic problem, then you probably want to multiply these out, and we will. But I'm not going to write the answer, because in general, there's going to be x's here, and you don't want to multiply it out. You just leave it as it is in factored form. 7 times 2 is 14 times, and then I'm going to group the 2 and the 5. That's a 10. 14 times 10 is the 140 that Brandon came up with. Right, so that is the LCD. But I'm not going to put 140 here. I'm just going to leave it in factored form. It's better. Step 4, convert each of the original fractions into new fractions that have the right denominator by multiplying each fraction by the right foo-foo. Remember, foo-foo was fancy form of 1. The idea is to multiply by what's missing. So let's come back up here. And I'm going to write that 9 over 28 again. Nine over 28. But I'm going to change the 28 by writing it as whatever's in the first circle, the left-hand circle. It has a 7 and a 2 and a 2. In fact, that's the stuff we came up with in purple, right? 7 times 2 times 2. And then we ask ourselves, how are we going to get from this denominator, 7 times 2 times 2, to the correct denominator, which is all the stuff in green? What's missing? It's a 5, right? That's the only thing that this blue denominator is missing to become green. So we're going to multiply here by 5 on the bottom. That's to make the right denominator. But if you multiply the bottom of a fraction by 5, what must you do immediately? Multiply the top by 5. That's the foo-foo that we introduce. So we bring in the 5 in the denominator because it's missing, and then we put a 5 in the top because that's what we have to do. So putting these all together, upstairs we have 9 times 5, which is 45, over. And then downstairs, I'm just going to copy this guy just as it is. I'm not going to multiply it out, but I'll just leave it like that. Victor. Because the only thing that I had to start with was 28. And 28 is 7 times 2 times 2. Yeah, you copy it from the factored form, and then you bring something in to fill it in to complete it so that it becomes the LCD. So that's good with that fraction. Let's try the other fraction. Somebody tell me it's just off the page. What was it? Something over 20? 3/20ths? So over here, 3 over 20. Okay, we already factored the 20. It's 2 times 2 times 5, right? So that's what we're going to write. 2 times 2 times 5. Nothing funny there. It's just another way to write 20. But again, the goal is to make it have the right denominator, the LCD, which is still here in green, 7 times 2 times 2 times 5. What is this black denominator missing to turn into the green? It's missing a 7. So we put a 7 downstairs by multiplying. But then what do we have to do right away? Multiply by 7 upstairs. So my new fraction, upstairs, I can do 3 times 7, that's 21. Downstairs, I'm just going to copy it in factored form, 2 times 2 times 5 times 7. Any questions so far? Okay, so I'm going to circle here in purple the two new fractions. There's the 45 over and the 21 over. And the original problem, was it an addition or a subtraction? We got 45 over, that stuff in green. And then addition, 21 over, stuff in green. So those are just our two circled fractions. What do you observe about those two denominators? They're the same. That's what we did. We did all that hard work to make these denominators the same. They used to be 28 and 20, different. Now they're both 140, although we're not writing it as 140. But those are the denominators that Brandon said we should shoot for. And if the denominators are the same, then what can you do with the numerators? We can add them because we have the same denominator. So upstairs, 45 plus 21. Downstairs, I'm just going to copy. Doesn't matter what order you put it in. And so what do we get here? 66 over 7 times 2 times 2 times 5. And a lot of times that's the end of the problem. In this case, you see that we can reduce. 66 definitely has a 2 in it. Maybe some other stuff too, but it definitely cancels with something in the bottom. So we've got our not quite final answer here. 66 over 7 times 2 times 2 times 5. And then if we want to reduce, gotta factor everything. Good news is the bottom is already factored, but the top has to get broken down. So the top is really, what, 2 times how much? 33. Let's keep going with 33. 33 is really what times what? 3 times 11. You guys buy the top is still 66? And now it's all multiplication, which means it's okay to cancel. So what goes away? One of the 2's. And so our final answer is just 3 times 11 over 7 times 2 times 5. Now I'm going to put here in a different color. I'll put it down here in blue. It's 33 over whatever we get, 70. But I'm going to like put 2 little lines through that just to highlight that you are not expected to multiply things at the end. If it was an arithmetic problem like this, of course you would write set 33 over 70. But all the problems that we're going to do, it is so much better to just leave it in factored form. So even though it looks really strange, that last thing we wrote in black, that is typically the way things end up when you're doing this with algebraic fractions. Okay, so it's a little bit of a process. In a nutshell, here's the process. Factor those denominators. Use that Venn diagram to figure out what the lowest common denominator is going to be. Then you take your old denominators and you make them the right denominator, the LCD, by filling in what's missing. And then finally, once you have the same denominator, you can combine the numerators. So that's the process. So let's give it a shot now, but with x's. So first one, 1 over 3x minus 3 over 5y. So I see it's subtraction. I see the denominators are different, which means we've got this whole process to do. So factor the denominators completely. What can you say about factoring 3x? Just 3 times x. It's already multiplication. There's nothing else to do, which is great. How about the other one? Just 5 times y. Nothing to do. I see 4 factors up there, 4 things being multiplied together. We are going to put those 4 things into the circles in just the right spots. So the first thing is a 3. Is there a 3 in the other guy? No. So where does that 3 go? In the left, middle, or right? In the left. So the 3 is there. Check off the 3. You see an x in the other side? Nope. So where does the x go? Also in the left. Done with that one. Next one is a 5. You see a 5 in both? Nope. Where does it go? On the right. 5 there. And the last one was the y, which is also only in 1. Not so atypical to have nothing in that space in the middle. It's totally fine for them not to have any common factors. Okay, so that means that the LCD is just the product of all four of these guys. 3 times x times 5 times y. And it's totally fine to change that to 15xy. That's what that's equal to. But doing that actually makes things harder in the coming step. So I would encourage you just to leave it. Don't multiply through. Multiplying through hides what's really going on. So we're going to write our original fractions, but factor denominators. So what was the first one? 1 over 3x. It's already factored, so nothing to do there. And then the other fraction was 3 over 5y. And it was already factored, so that's nothing else to do there. But now we got to multiply by foo-foos. You got to make these denominators the right denominator, which is sitting there in green. So looking at the first denominator here, it's currently 3x. If I want to make it green, what is it missing? 5y. So downstairs, I put a 5y because that will complete the denominator that we currently have. But you can't go around doing that without immediately doing what? Same on the top. So there's a 5y up there. And then looking at the other denominator, it is currently 5y. It needs to be green. What's it missing? 3x. So we put 3x downstairs because that will give us the right denominator. We put 3x upstairs because we're required to. Okay, so then our new fractions, looking at the first fraction, I'll copy the denominator just like it is. And then I'm going to multiply the numerators together. We know how to multiply fractions. It's straight across. 1 times 5y is just 5y. And then the next one, I'll copy the denominator just like I see it. And here, up on the top, we actually are going to do the multiplication. So just multiplying these two guys together, 3 times 3x, it's really the only place that we're going to multiply. And we're going to write 9x. There. From way back in the beginning, what symbol was between two fractions? Subtract. So we're going to subtract here. Subtracting these two guys. Look carefully at those two denominators. What do you see? They're the same. We built those denominators to be the same, which means we get to mush together the stuff in the numerators. So one denominator, 3 times x times 5 times y, because they're the same. And then we can smush together the two numerators, 5y minus 9x. I'm going to put something in which is not relevant here, but oftentimes is necessary, so we'll just put it. And then basically I think we're done. Our answer is just 5y minus 9x. We can't combine those at all. Divided by, and then we'll write our denominator. Of the numerator or denominator, which is the one that has stuff that's cancelable in its current form? Denominator, because it's all multiplication, right? The top is a subtraction problem. If you could factor the top, then you would turn it into multiplication, and maybe something cancels. Is there anything you can factor out of both terms on the top? No. It doesn't look like an x squared or anything familiar looking for the factoring tools that we've got, so we can't factor the top, and we're done. I guess I would say this is the only place I would actually multiply. I would finally do the 3 times 5 downstairs. So my final answer would look like this. Probably, yeah, the only place you multiply out on the bottom is if you have 2 numbers. That's the only thing I'm multiplying. But if I had like x's in parentheses and other x's in parentheses, I would never in a million years multiply them together. The only thing to multiply are the numbers. And hopefully that's rational, because if you had like a million x's multiplied by a million x's and you distributed, it would get bigger, right? Whereas multiplying 3 times 5 takes 2 numbers and makes them a single number, which in some sense is simpler. Okay, one word of caution. Over here, can you cancel the 5y's? Maybe put a 1 up there and a 1 down there. Is it legal to cancel those 5y's? It's all multiplication. Totally legal. Should you cancel the 5y's? No. Why not, Alex? Yeah, you're just going right back to where you started. What's good about the fraction in its current form? It's got the right denominator. But if you cancel the thing that you work so hard to put there, you're just going backwards. So it's not wrong, but it's also not encouraged. You'll always have that opportunity, because you're always going to put in a foo-foo. It's here in green. So don't put it in and then in the very next step say, oh, goody, I can cancel something. You can, but you shouldn't. Next question. Can we cancel here this 5y with this 5y? Why not? There's subtraction. You cannot cancel the 5y on the top because there's subtraction. But you will always have this opportunity, because there's always going to be foo-foos floating everywhere. And in fact, inside of this 9x, there's a 3x. You have plenty of opportunity to cancel. You can't. In one case, you shouldn't. In the other case, it's not allowed. Okay, moving on to the next page. Let's try another one of these. All right, this one we're going to skip. Nope, let's do this one. Let's do this one kind of quickly. Factor the denominator. All right, so I see a subtraction, so I'm really hoping that the denominators are the same. They're not. So we've got this big process. So you're going to try to factor 2y minus 1. Anything you can factor out of both? Nope. Is there any other kind of factoring that we can do to 2y minus 1? There's no way to factor that. It's just 2y minus 1 as an entire thing. And this same guy over here, y plus 1, same story. There's nothing to factor out of both, no other kind of factoring that works. It is what it is. So then when we come down here to putting things into our circles, it's trying to build the LCD, I'm going to throw parentheses just to highlight that that 2y minus 1 is one big thing. And the y plus 1 is another big thing. So when I go to check things off, I cannot pick and choose. I can't go in there and pull off the 2 and pull off the y and pull off the 1. That is one complete thing. So is that one complete thing in the other guy? Does it appear as an exact copy in the other denominator? No. So that one complete thing goes all on its own in the one circle. And that takes care of the whole thing here. And now it's time to look at this whole thing. Is there an exact duplicate of the entire parentheses, but over in the first space? So where does that y plus 1 go? On the right. In parentheses, just like that. And I know this probably looks a little bit funny to have the entire things. All of a sudden it's subtraction. But look, could you cancel these y's right here? No, because you can't pick things apart in that bottom, right? The 2y minus 1. You cannot selectively choose to go in there, which means the 2y minus 1 is in some sense a fundamental building block. You can't pick it apart. So it's the same idea. You can't pull it apart. You can't take it as a 2 times a y and then a subtract 1. You can't separate them. It is indivisible. And so it's got to go as itself in the circle, which means that when it comes time to write the LCD, we're just writing in parentheses 2y minus 1 times y plus 1. This is kind of similar to something like this, 3/4 plus 2/5. What's the lowest common denominator for those fractions? 20. How did you get 20? Multiply them. In some cases, the worst possibility is where you just have to multiply them. 4 times 5 gives 20. That's exactly what we have in this fraction, this thing with the y's. What's our lowest common denominator? It's just the product of the two things. They have nothing in common, so the denominator that we're going to build is in some sense the worst possible one, where you just have to bail and multiply the two. You can always do that. You can always multiply the denominators. And in fact, that's exactly what ended up over here too. 3x times 5y was the denominator. It's going to turn out taking that as a strategy where you just always multiply the denominators is a bad strategy. And you'll have to trust me on that. We'll see next class why it's a bad strategy. Yes, you can always do it though. Okay, so let's keep going down here. So let's write the original fractions. Somebody help me out. What was the first one? Was it y over 2y minus 1? And then the other fraction was 2y over y plus 1, like that. Okay. And now we're going to fill in some foo-foos in order to build the correct denominators. So looking at the first fraction, it currently has a 2y minus 1 in the denominator. We're trying to build this green thing. What is the blue guy missing? Y plus 1. And so we put here y plus 1, and then right away, y plus 1. Okay, and I'm going to throw something in here, which again, I encourage you to put, but these guys are getting quite complicated. And so I'm just going to throw parentheses around everything just so we really understand that everybody, that those are like 4 completely separate entities. And if we're going to multiply things through, it's all distributive. Moving to the second fraction. Say it again. 2y minus 1 is what we're missing, right? Current denominator is y plus 1. Want to make it green, 2y minus 1. Downstairs because that's what we want. Upstairs because we have to. And again, parentheses everywhere. Okay, so we've got our fractions. I'm going to copy that first fraction's denominator, 2y minus 1 times y plus 1. And now I'll say something for the first time today. When we're figuring out what our new fractions are really, what they really are, you never multiply downstairs. So 2y minus 1 times y plus 1, you could FOIL or lobster claw or whatever you want to call it. But we never do. Never multiply out downstairs. But take a look upstairs. There's a y and there's a y plus 1. And we always multiply upstairs. We'll see why there's this distinction in a little bit, but for right now, you just have to take my word for it. But let's go ahead and distribute or lobster claw that y into the y plus 1. So what do we get first? Y squared plus y. Done with the first fraction. Then we're looking at the second fraction. What did I say about denominators? Stay the same. So I'm going to copy that denominator as it is. And what about numerators? Always multiply. So we're going to distribute that 2y into the parentheses. What do we get? 4y minus 2y. 4y squared minus 2y. Okay, I was real happy having parentheses before, so I'm going to throw them in here again. Might not matter, but we might need them, so let's just put them. The original problem from the top, is that an addition or subtraction? Subtraction. So I'll put a subtract sign right there. What do we notice about these two denominators? They're the same, which means we can mush together the numerators. So one big fraction, 2y minus 1 times y plus 1. You can swap the order if you want. And then I'm just going to copy the stuff that's upstairs. Y squared plus y minus 4y squared minus 2y. Still with the parentheses. Without those parentheses, we're going to get it wrong. Does everyone see how to go from the previous step to the one we just wrote? Same denominator, so that means they mush together and become just one copy of that denominator. But upstairs, you do the addition or subtraction. And so when it comes time to do this subtraction, so we'll just do a tiny bit of this in our heads, but we imagine that minus sign coming in and hitting both of these guys, right? And so the first thing we need to do is y squared minus 4y squared. What is that? Negative 3y squared. That's that guy minus that guy. And then I see a y, so we're here, minus negative 2y. Minusing negative 2y is the same as adding 2y. So this is really y plus 2y plus 3y. And the denominator gets copied. Questions on that step? We kind of skipped a step. We did this part in our minds, this subtraction here. So that subtraction is going to apply to both of these guys. It's going to mean minus 4y squared. That's easy enough. But it's also going to be minus negative 2y. And so in my mind, I envision that as a plus 2y. Subtracting a negative is like adding. So all we did then was combine terms. Y squared minus 4y squared gave me negative 3y squared. And then that y plus the 2y gave me the 3y. Remember how I said we treat numerator and denominator differently? We never multiply out on the bottom, but we always multiply on the top. So we just saw why we multiply on the top. We were able to combine terms here because that was just some y squareds and that was some y squareds and some y's with some y's, and we could combine them. But imagine if we hadn't distributed, if we just had this problem here with a big subtraction between. Sure, they've got the same denominator, but can you combine some of those guys with some of these guys? Well, I don't know. I don't know what they really are. So I have to kind of unpack them from the parentheses. Do we buy that? Like multiplying that y through told you what you really had. Oh, you had some y squareds and you had some y's. And then we did the same thing over here, distributing this guy. And oh, look, we've got more y squareds and more y's. So we're going to finally smush them together. That's why we have to multiply together on top. Okay. So good news is most of this is done. The bad news is it's not all done. Because if we can cancel, then we need to. Can we cancel now? Like, could I cancel a y on the top with a y on the bottom? No, because upstairs is an addition problem. Things downstairs are cancelable if you can find something that matches what's in either of the parentheses, but we got to factor upstairs. So what comes out of what's in both of these guys upstairs? The 3 and also a y. So we're going to pull that 3y outside and have one thing in the parentheses. Okay, what's left from the first term? 3y is now outside. So a negative and a y. That'll give you your negative 3y squared. And then plus 1. Good. And then copy that denominator. Okay, we factored as far as we can. I see something up here that looks quite similar to something down here. And the question is, can they cancel? So are they exactly the same? No, so we can't just straight cancel them. But a little light bulb goes off in my head. It says, oh, maybe this is the a minus b, b minus a thing, where we can cross them and bring in a minus 1. Is it? No. The a minus b and the b minus a, what's in between both of them is a minus, right? A minus b, b minus a. But downstairs, what's in between? A plus. There's just no way. I mean, like it is not that pattern. Yes, they both have y and 1, but there's no way the signs are going to work out for us to use any kind of pattern we've seen. So this is our final answer. Okay, so we're going to skip the next page and jump to the group activity, which is right there. So last thing I'll say about these guys, they are hard, they are long. I recognize that there's a big process that you're going through to follow them. So they are the last topic of the semester, and in some sense it's because we recognize they're really hard. Also, it means that you guys are so tired and beaten down by this point, you can't revolt because these problems are so hard. You just have nothing left to, kind of throw back at me. So they're here at the end because I know you're too weak to fight back. So do what you can with these problems that I fully acknowledge are really hard. Raise a flag if I can help.